I looked at the code that we were debugging a little bit more last week, and it doesn't do anything serious with OpenGL, but it does have some color calls to various color modules that are OpenGL related. So we'd have to sort of make a different version of that isosurface routine. I think if we wanted to strip all the color stuff out of it, I think it would be tricky to strip the OpenGL stuff out of it without breaking something. So I think it's probably something that I'll sort out with Eric, and then if we come up with a new system that can be called from Python to deal with the isosurfaces, then we'll present that sometime later. Just as a note, I'm going to be on an airplane myself next Thursday at this time, so we'll have to skip a week in these things next week. But I'll plan to continue again the week after that. So does anyone have any issues they want to discuss before I come up with something random? No?
So I had asked about talking about the Wiener filters and seeing if we could approximate something like IsoNet is doing. I don't know if that's
right.
Too big of a topic or too in depth. I did go back and reread those papers.
Okay. Did you figure out what they were doing?
Yeah, so they reference the warp paper, and the warp paper talks about deconvolution. Basically, they're saying that low spatial frequencies are not as visible, don't have as much contrast. And so they're doing something to boost those spatial frequencies. Unfortunately, most of the math was a little bit over my head. I'm assuming that because there's not much of a phase shift at low spatial frequency, that's why there's not as much contrast.
Okay, so I if you're talking about very low spatial frequencies, then there isn't much contrast. All right, well, so let's talk about some CTF stuff. That sounds like a worthwhile topic. Let's see, which screen am I sharing? Do you see mountains?
Yes.
Okay, good. I'm sharing the right screen, I guess, then. All right. Maybe a little too big. That okay? All right. Let's conda activate. Let's do that to start. All right, so we've got this Ctf simulation program, right? This is a very simplistic Ctf simulation program. It can do some things like defocus, but it does not do any higher order artifacts or anything in the microscopes. It basically simulates a standard CTF model that you'd see in any paper dating back to like the 2000s or something. I guess what I'm saying is there is a deeper level of sort of math that's involved in image formation, but we won't talk about that level. So basically, we have a defocus and a B factor, right? So the defocus governs the spacing of the peaks, which is nonlinear, so it's not just a sine wave; it's a sine wave with a nonlinear x-axis. Then you get the B factor, which is how quickly the curve falls off. If we adjust the B factor like that. And the term B factor, of course, comes from X-ray crystallography, where B factors are used to be the individual molecules in the atom are vibrating, and they may be vibrating a lot or they may be vibrating a little. But if they're vibrating a lot, then you can't determine their position as precisely. That it'll always look like a smear in space, and you can compensate for that in various ways. But the impact of that local vibration, it will be treated as sort of a Gaussian distribution of positions that the atom takes in space, and then that turns into the so-called B factor, which is what that looks like in Fourier space. So basically in Fourier space, that causes a decay with spatial frequency. So let me present this as intensity, which is what we usually are looking at in cryo-EM. So as the atoms vibrate more and more and more, the decay in Fourier space becomes faster and faster and faster. Now, B factors that you would see in crystallography are tiny compared to this. In cryo-EM, a typical B factor on a modern Krios with a really nice detector on it or something might be in sort of the 50 to 100 range or something like that. If you go and look at a 200 keV scope without a field emission gun, or something that you use for screening or something, the typical B factor from an instrument like that might be 2,500 or 4,000 or something like that. So if we put 2,000 in there or something, right, you can see the B factor decays already at 15 angstroms or something. So typically we'd be more in this range. Then here we've got defocus difference, defocus angle. That would be for astigmatism. So if we put in a significant defocus difference, you can see how now the 2D CTF curve here becomes elliptical, and the defocus angle, we can adjust the orientation of the astigmatism and that sort of thing. But typically we'll just sort of assume there's no astigmatism. Then we have amplitude contrast, which is defaulting to 0 here. Now you'll note here if I grab the amplitude contrast slider, it's also changing the phase here. So you can, the thing that we call amplitude contrast in cryo-EM is basically just a phase shift. It's not the real. How do I say this easily? All right. So when electrons pass through a specimen, two things happen. The electrons undergo a phase shift. Every time an electron interacts with another electron, its phase gets retarded slightly. So the phase gets shifted a little bit in time. So the electron takes longer to get through the specimen effectively. It's kind of like an index of refraction or something like that. In fact, the analog is basically exactly an index of refraction. So basically, it's a slowing down of the electron beam, and the more interactions it goes through, the more it gets slowed down as it passes through the specimen. So that's one thing that can happen. The other thing that could happen is that an electron gets absorbed, or basically doesn't get through. It impacts something and then gets scattered off in some funny direction, and it never makes its way to the detector. That could be. So normally when we're talking about cryo-EM imaging, we're talking about imaging that happens due to the elastically scattered electrons. So the electron interacts with another electron, and it comes out the other end with the same amount of energy. It's just delayed in time a little bit. So that's the traditional image formation electrons that you get. Then any electron that undergoes inelastic scattering, in other words, it loses energy when it scatters or gets scattered off in a funny direction, is considered to be sort of absorbed. So if you have an electron microscope that has an energy filter on it, the idea is that it's getting rid of all of those electrons that get scattered, but they don't have the right energy anymore, that sort of thing. They can't form a proper image. If you don't have an energy filter, those things still wind up hitting the detector and they show up as extra noise. If you do have an energy filter, then they get eliminated completely. Okay, what does that mean? So any electron that you lose, that's what you'd normally term amplitude contrast. But that's not what cryo-EM means by amplitude contrast. So if you talk about light optics, you have the same sort of concept. You have the phase contrast, which is the refraction. So if you put something through a glass lens, put light through a glass lens, the index of refraction is what's responsible for the image formation. That's the same thing, the same sort of thing that's happening when we talk about phase shift in electron imaging. But then in optical microscopy or optics in general, you also have the concept that you might be absorbing some of the light. So if you have a piece of exposed film and only some of the light gets through, there's that amplitude decay. Now the difficulty here, the trick when you're trying to do optics is that the phase retardation issue or the light refraction issue are linear with respect to thickness. If you pass through something that has a thickness of 2, it's going to undergo twice as much of phase shift as something that has a thickness of 1, right? Whereas if you talk about amplitude change, so loss of electrons or loss of photons, that sort of thing, that is an exponential phenomenon. So if you have something that's twice as thick, you're going to lose 4 times as many electrons than if you have something that's a thickness of 2, you lose 4 times as many electrons than if it had a thickness of 1, and it scales exponentially the thicker it gets. All right, why did I bother explaining all of that? Well, the way amplitude contrast is treated in electron microscopy is kind of wrong. It's an approximation. So in electron optics, we talk about the weak phase approximation, and the weak phase approximation is basically assuming that there's no absorption, that everything that we're looking at is elastic scattering, and our images are formed by phase shifts. And the pure weak phase approximation would correspond to an amplitude contrast of 0. Okay. Amplitude contrast is what you get if you make a sort of a first order approximation, or maybe it's even a 0th order approximation of what happens when you lose electrons to the CTF of the signal that comes out. You're not actually treating it as an exponential decay. You're kind of doing a linear approximation of the exponential decay. So you're sort of assuming that if any electrons are being lost, they're only very, very rarely being lost. And we can then still sort of approximate it as if it were a phase shift. And if we approximate it as a phase shift like that, then it becomes a phase shift in the CTF curve. So when you put in this amplitude contrast, all it does is it causes a shift of the phases here. What I'm trying to say, though, is in reality, if you have an exponential decay based on relative thickness of the specimen, you can't model it this way after all. The assumption that goes into amplitude contrast, the way it's done in electron optics, is that if you had something with something that absorbed 2 times the number of electrons versus something that absorbed 1 times the number of electrons, if you switch the order of those 2 layers, it wouldn't have any effect. Whereas, sorry, I didn't prepare in advance for this, so I'm just thinking through the best way of explaining it. If you think about a layer that has a pattern in it, right, and then you have another layer that's absorbing some number of electrons before the pattern, you're going to get different results out if you sort of absorb the electrons first versus absorbing them second.
So if I'm understanding this correctly, there's multiple layers of scattering effects where an electron will scatter and then hit something else and scatter again.
Yeah, I mean, yeah, you're talking about the theory the right way. I guess what I'm saying is that in the theory we're assuming that the effect is linear, and it's not linear; it's exponential. Anyway, so you have this amplitude contrast effect, and we call it amplitude contrast normally. Then you'll also talk about having, say, a phase plate in the microscope, right? So if you put in an ideal phase plate, what it does is it introduces a 90-degree phase shift. that would correspond to 0.5 here. Now, if we look at our CTF curve over here, so let me go ahead and do this. I'm going to turn the amplitude, set the amplitude, so I'm going to set the B factor to 0, so we don't have any decay, and I'm going to set the defocus to something smaller, so we just the ripples aren't getting undersampled or something like that. Maybe 0.4 or something. Yeah, that's pretty good. Okay, so now we have our CTF pattern here, and now we're going to set our amplitude contrast back to 0. So this would be what we get from a pure phase contrast image. And you can see that the contrast at the origin here, right, at very low spatial frequencies is 0. Right? So you actually get no signal at all at very low spatial frequencies. Then as you work your way up to this first maximum of the CTF, which in this case is at 12 angstroms, then you start getting signal. So in the olden days, before any phase plates existed, your way of getting low resolution contrast was by going to a higher defocus, because as you go to a higher defocus, it shifts that position of that first maximum to lower spatial frequency. So now at 3 microns under focus, let me make more samples here so this looks better. Yeah, ignore the patterns there. Those are just screening patterns that you're seeing there. This is the actual CTF pattern that you're sort of seeing there. Anyway, so if we go 3 microns under focus, then this first maximum where we get a lot of contrast is at like 35 angstroms. If we go to 1 micron under focus, then the first maximum is at 20 angstroms. And if we go to where I was before, 0.3 microns or something like that, then it's all the way down at 12 angstroms. So between here and here, the contrast gets stronger the higher the resolution gets, and you don't have anything out in here. Now that's with no amplitude contrast. Now the typical specimen that you put in the electron microscope, typical single particle specimen, is normally estimated to have somewhere around 10% amplitude contrast. So the signal you have at the origin is no longer 0, but it's still kind of small. It's still something like 10% squared, so it's like 1% in terms of intensity here. It rapidly scales up, right? I mean, you don't have 0 at so if the maximum here is at 28 angstroms, you still have a significant amount of signal at 50 angstroms, and still have a decent amount of signal at 60 angstroms, etc. But it's rapidly fading as you get to lower and lower resolution. So the idea behind the phase plate is you retard the central beam, the electron optics by exactly 90 degrees, and then that causes this phase shift here, which does this. It shifts it so the signal is at a maximum at a spatial frequency of 0. So now this is all the way up at the highest percentage that it could possibly be, and now you actually want to get as close to focus as you can. You basically want to get down close to sort of Schetzer defocus here, because you no longer have to worry about correcting doing your CTF corrections here. You don't need all those oscillations in there to correct the CTF. You can just basically go really close to focus, and then maybe do a little correction on the overall amplitudes in your images or something like that. In reality, what people typically do if they're using phase plates is they still go a little out of focus, so they still get some CTF oscillations in here, and they still do their phase flipping, but they'll put the first 0 out pretty far, pretty high resolution.
Can I ask a couple questions here?
Yeah, please go ahead, because I'm just spewing out lots of random stuff.
So the work paper, they start off talking about the deconvolution. They say without a phase plate, the CTF will be dominated by its sign component. That is, it will have very little contrast in the lowest spatial frequencies. So I think that's what you're describing here. And so that, if I'm understanding this correctly, that's because at the lowest spatial frequencies, the beam is effectively passing through the sample without any sort of phase shift, and that's why it starts off at 0.
At the lowest spatial frequencies, yeah, that's right. The phase shift is not producing any significant contrast in your images.
And so that 90-degree phase shift forces you to start off closer to 1 because 90 degrees is going to give you.
Well, it's a 90-degree phase shift. It's a 90-degree phase shift only on the unscattered central beam. So what you're doing is producing a relative phase shift between the unscattered central beam, which is basically at infinitely low resolution, and the rest of the image that comes out. What it does is it sort of produces an artificial amplitude contrast between that unscattered beam and the stuff that gets phase shifted normally by passing through the specimen. It's hard to sort of hand wave your way through. You kind of have to work through the math to exactly see where it falls out. But the effect on the CTF is this: that it basically takes that first zero at the origin and it basically makes it a maximum. Now, when you say you're going to do a 90-degree phase shift, that's the other thing that I wanted to point out, which is that the people sort of often treat this as, oh, well, what was the phase shift of my phase plate? Because if you're using one of the FEI style phase plates, where the phase shift changes with every image, you have to actually estimate how much phase shift you're getting. But they have sort of two parameters. You have the amplitude contrast of the specimen, and then you have the phase shift of the phase plate. But in reality, mathematically, those two things are doing exactly the same thing. There's only one parameter, which is how much phase shift you got. And some of that may be coming from the specimen, and some of that may be coming from the phase plate. But so what you actually want the phase plate to do is more like an 80-degree phase shift. Or an 80% amplitude phase shift that would get you 90% amplitude contrast, and then you get the rest of your amplitude contrast from the specimen or something, but you don't have tight control over it. That sort of thing. Anyway, the point is you'd like to get to a situation ostensibly where you're first at low resolutions you have a maximum instead of a minimum. Now, something which has not widely been considered in the field is that there are some negative impacts of doing that too. If you do this, you get this massive contrast at low resolution because you also have this B factor, right? So you've got this B factor, so this fall off at high resolution. So if you have no amplitude contrast, it looks like this, okay? So you're getting a lot of signal in here, and a lot of signal in here, and a lot of signal in here. But if you now have this 90-degree phase shift, this sort of phase plate contrast, you've got a lot of signal in this really low resolution stuff here, but you proportionally have substantially less signal out here at high resolution. You're sort of stealing a bunch of the contrast that you would get at high resolution for low resolution.
It's almost acting like a low pass filter in a way then.
Well, it's not. So it's not actually lowering the contrast you get here. It's only lower with respect to the overall contrast that you're getting out, right? So the contrast in, say, this 8 angstrom kind of peak here is smaller with respect to the total energy that's being scattered due to so much of it being in this peak here. And you'd say, well, what's the problem with that? Well, the problem with that is the fact that we have a limited number of electrons. So if you're only, if all of the information you're getting in one region of your image is coming from 30 electrons, and a lot of the energy that is being used up in this very low resolution regime, then you may actually wind up effectively getting less energy out at high resolution. The shot noise will start taking over. And this is something that really hasn't been taken into account very much in the people who have played with phase plates and that sort of thing. There's an additional factor, which is the structure factor of the specimen, right? So what we're looking at here is the pure CTF, but in reality, what you see for the specimen is going to be the structure of the specimen, the Fourier transform of the pure specimen image multiplied by this. And there's a very strong peak at low resolution in the specimen structure. So that further exacerbates the effect. So when you start using the phase plate, people have historically found that they use the phase plate and wow, look, I can see this beautiful high contrast image in my specimen. I can see where everything is. It looks gorgeous. But then when they try to solve the structure, they can't get out to high resolution. And there were a lot of theories going around that, oh, it's due to the fact we can't accurately estimate the CTF, or it's due to the fact that the phase plate isn't a perfect circle. It's got some structure to it, and that's causing some distortions, which are impacting high resolution. Or there's all sorts of theories. My theory is that it's actually due to the fact that you've stolen all of the high resolution information. You've stolen all of the power available for that high resolution information in the low resolution regime. Anyway, all right. What we were actually, I think, talking about, I guess, was the what sort of filtering you might apply to an image to improve its contrast. So when we look at sort of this pure CTF here, we've also ignored the noise, right? So really, it's not a question of whether we have signal here. Even if we're in the situation where we only have 10% amplitude contrast, there's some signal here. It's just, it's just only 1%, right? And here there's 3, 4, 5, 6% or whatever. So as long as you don't have any noise, it's fine. You still have a perfect signal to noise ratio here. But then as soon as you add noise in, now the signal to noise ratio gets bad here. And then you'd have a strategy for, well, how should I be filtering this low resolution stuff to try and make the image have optimal contrast? So normally when people sort of historically talked about Wiener filtration, what they were talking about doing was dealing with a higher resolution regime. You have your image that came out of the microscope and it's noisy because there's a lot of noise, and it's multiplied by the CTF. So you can make it less noisy if you actually filter out the stuff here and you're around the CTF zeros, right? So your signal to noise ratio here, I guess we don't have any, I don't have any noise slider in this simulation program. If you added noise to this curve, right, then your signal to noise ratio here would be 0. Your signal to noise ratio here would be as high as, say we had 0.1 noise all the way across. So the signal to noise ratio here would be like 6. The signal to noise ratio here would be 0. And so you'd like to filter the image such that you sort of preserve the information in proportion to the signal to noise ratio. You want to keep this information very strongly. You want to completely filter out this, and you want to somewhat filter out the stuff in between here. You could take that to the low resolution end too, right? Here you could sort of filter out some of this stuff somewhat, and maybe make the image look a little bit nicer. But that's actually a really tricky thing to do, because it's hard to sort of separate the contrast that's coming from ice gradients and other low resolution noise stuff from the stuff that's coming from actual features of your specimen. So it's not really very separable, and it's not really straightforward to do. So that's why you might want to use like a denoising filter. If you use a deep learning strategy, right, a denoising deep learning strategy or something, would be doing something kind of akin to a Wiener filter. It would be basically trying to answer the question, well, here's my noisy input image, and I would like to make that noisy input image look as much like a image without noise as I possibly can. So you could put it through a denoising network to try and accomplish a task like that. And that would be akin to what people mean when they say Wiener filtration. Try to get rid of as much of the noise as we can, knowing that you can't get rid of all of it. There are Wiener filters available in EMAN, which you have to determine the CTF before you can use them, but they are usable. I'm just trying to think of the best way of demonstrating that. Maybe let's just look at one of the workshop demos.
where I actually got stuck on the EMAN Wiener filters was how to enter the CTF, or the defocus rather.
Yeah, so normally what you would do in the EMAN workflow would be you determine the CTF parameters as a first step. So all the particles would already have it, right? So if you're looking in the particles folder, you have several different types of particle objects. You have the original raw particle stack, right, which looks like that. Then you would have the like the low pass filtered version, downsampled low pass filtered version of the particles. And then you have the full res particles, which are the original particle stack, which has been phase flip corrected and circularly masked. So these particles have embedded CTF information. So if we look at the control panel here, you can see CTF there. Oh, and my Mac font is messed up, so you can't actually read those. If we, let's do it this way. If we look at the header of any one of these particles, we can see there's a CTF object there, which has defocus, B factor, amplitude contrast, all that stuff from the CTF fitting process.
Okay, so I was trying to do this to a tomogram, so that's probably why.
Yeah, so there is no such thing as the CTF of a tomogram, right? Each tilt image will have defocus parameters associated with it. If you're talking about the zero tilt image, then you can have one set of CTF parameters, which are pretty good for the entire image. But then if you have a tilted image, then of course there's a defocus gradient as you work your way across the image. If you collected sort of the perfect tomogram where the defocus along the tilt axis didn't change at all between images in the tilt series, so you just set the defocus in the middle of the tilt series to be 2 microns or something like that, and then you tilted, then you would actually expect the defocus to vary with Z in a very uniform way, but that's not really what happens, right? Really, when you collect data in the microscope, the mean defocus of each image is different. So if let's take a look at a tomogram example, a tomographic tilt series example. So if we go to Tomo, yeah, okay. So this is from the tomography tutorial. So here we've got the tilt series. This is the standard ribosome data set that we use for the tutorial. So if we just look at this tilt series, oh, should have done it the other way. Hang on. Show 2D. And we can, work our way through tilt series. So when you run, so if we look at the images in the tilt series, you will see that they do not have CTF in the header or anything like that. Okay, these are tilt series that I've already reconstructed, right? So if we look, we look in tomograms, we've already got, well, all right, I've only reconstructed one of them, but we've already got a reconstructed tomogram, which was done with CTF information known. Right, so there's our tomogram, there's the layer of ribosomes in the middle, and that sort of thing. So what happened when we determined the CTF parameters? Well, the CTF parameters get written into the info folder, and then each, I only ran it on Tomo A, because I only did the tomographic reconstruction on one of them. There are tilt parameters, there are, I guess, all right. I guess maybe we didn't do that in this project, but we'll go ahead and do it. It only takes a minute.
So what is the defocus number that?
Well, it's not just going to be, you mean, oh, sorry, go ahead, ask the question.
So, I mean, if I run the CTF estimation, I'll get a defocus number out for the tomogram that'll be under the, I'll see it in the analysis. So what is that number? Is that just an average?
So that's the defocus in the middle. If you just see one number for the whole tilt series, then that's going to be the average defocus in the middle of all of the images.
Okay.
But the actual information that's stored is actually a per image defocus in the middle, and then it knows the tilt of the images, so it can compute the defocus at any point in the volume, or sorry, any point along the tilt series. Let's go ahead and run it, then we can see the information that's stored. So I'm just going to run Ctf estimation. We'll just run it on one tilt series. So we need to give it the standard parameters here. The defaults are usually fine. Sometimes people try to get closer than 2 microns under focus when they're collecting their tilt series. So if you do that, you need to take that into account in the search range. This is used if you have a phase plate. That's phase shift range. Voltage, C sub S, assuming you don't have a C sub S corrector, that's for Krios. Yeah, that's about it. So we'll just, oops. Yeah, I launched it twice. No, maybe not. Oh, there we go, it's wrong. Okay, we'll just wait for it to finish. It only takes a second.
I guess at some point, once I have formulated better questions, I'll write them an email and ask what they're doing. But I'm very confused how you can just apply one defocus to a whole tomogram.
You can't.
And then use that to construct some sort of Wiener filter.
No, you really can't. I understand you say that's what they're doing, but
those are the inputs I'm presented with. I'm not sure exactly what they're doing. It's not clear to me. So
you mean those are the inputs that you presented with in Hong's tomography program?
Yes.
Yeah. Phil, do you have any input on that? I know you tried to run it. Maybe not. Are you there, Phil? Okay. Yeah, so I would agree with the question. You could do something sort of at low resolution, right? And that may be all they're trying to accomplish. So, if you look at okay, it finished that, but let's go ahead and so if we just think about this again, let me put it back into intensity space here. So focus on just this regime here. Let's set the amplitude contrast to 10% or something like that. If you play with the defocus a little bit, right? The amount of impact that's going to have in here is not all that great. The amount of impact it has here is tremendous, right? Because you're shifting the position of the 0. So if you go from 1.5 to 1.9, you've gone from 0 signal to noise to 1, right? It's extremes. But if you're looking here only at the low resolution regime, then playing with the defocus has an impact, but only has a modest impact on the signal to noise ratio. So if you're trying to do some sort of correction in here, you might make a sort of a hand-wavy argument that that if you just have sort of an estimate of roughly what the defocus is, you can still make some sort of correction and have it come out kind of okay. I don't know that that's what they're doing, but that's my best guess. All right, so if we look at this here, you can see each of these ID numbers that came out is the ID number of a tilt. Right, so this tilt series had a full 60 tilts or 57 tilts in it. So then you can see the estimated angle, or the known angle for the tilt, and then the defocus value that it provides here is the defocus in the middle of the tilt. So if we then look at what's stored after you've run that program, we should now see in the info folder. Oh, I see. It looks like I actually ran it on more than one. That's fine. Doesn't matter.
So then it should just be.
Oh, sorry. Go ahead. Nope.
It should just be some trigonometry to figure out the defocus at any point on that tilt, then, right?
Yeah, more or less. You're going to assume that the tilt number you have is accurate, and you know what tilt axis you're using, so you're going to assume that that's accurate as well, so that it's just basic geometry. So if you look now at this info file, this Tomo A info file, after we ran the Ctf estimation, you will see in that file there is now a C sub S and a defocus, and you'll notice the defocus isn't a single value; it's a list of values per tilt. Okay. And then there's also going to be a phase. So if you were doing the phase fitting, then you would see some amount of non-constant phase shift here as well. So the voltage is constant, the C sub S is constant, the defocus will be per image, and then the phase will also be per image. If you wanted to get access to that from Python, since we're supposed to be talking about Python, we would just say JS equals JSON open dict info slash what was it called? There we go. Tomo A. I'm not sure. I'm not sure what file name was actually used. So data. Shop Tomo Tomo A underscore info.json, right? Oh, not JSON open dict, it's just JS open dict, sorry. And then JS is one of these dictionary-like objects. And we can see the keys, and the keys will include all that stuff we saw in the browser. So if we say JS defocus, there's your list of all of the defocus values for that particular tomogram. So technically, the way I should have gotten this name is actually there's a function info underscore name. And then you can give it the name of the image file that you were working with. So in this case, like tomoa.hdf, and that would return info tomoa. It'll return the name of the JSON file. And I think that even works right if you give it like tilt series / right. So you can give it a full path to an image file, and it'll tell you the name of the file that will be used to store metadata for that image. Okay. Now the reason we have these separate info files and we don't just store them in, say, the header of the image or something like that is because because images like this may progress through the project, right? So this was a set of tilt series. Then that turns into a tomogram, and then that tomogram may produce a set of particles which are associated with that tomogram. So this info file contains information which is relevant to all of those different stages of analysis. With this Tomo A serving as the name of that particular image or tomogram that relates to all of that data. So when we store subtomograms that were extracted from the whole tomogram, those would be also stored with the name Tomo A in the header. So you'd put all of the subtomograms from one particular tomogram in one file, and you'd put all of the ones from another tomogram in another file, and then you'd use the LST files link those different files together into a bigger virtual file. But
If I
anyway,
make
so yeah, go ahead.
if I make an EM data object of the image file, can I just pass info name that EM data object to get information about it?
No, because the EM data object doesn't always know what file it came from.
Okay.
There is a parameter in the header, so if we read an EM data from a file, so let's do that. Let's say A is equal to EM data series como a.hdf. So there is a header item, which is data source, I think. Oh, where is it? Oh, there it is. Source path.
Source path.
Source path, which will contain the name of the file that it came from if it was read from a file. But if we do, b equals test image and make a file just computationally, then obviously it can't have that sort of information in the header. Right, because it was never written to a file or read from a file. But so yeah, if you had an image that you read from a file, then yes, you could call info name on. So we could say info name a dot a of, like that. That should be okay. So you can't call it with just the EM data object, but you can call it with the correct header item from it.
Okay, that makes sense.
Right. So right. So that gets so once you've opened that JSON file, you can get access to all of the elements. Be a little careful, right? When you open those JSON files like that, if you have this JSDict object, if you modify the JSDict object, it will immediately write the stuff back to disk again to that file. So if I say JS of X is equal to testing, and I quit my program and take a look at info como A, you'll see that there's now an X testing element stored in that file. So you could easily overwrite important existing metadata by just modifying that dictionary, right? So if you modified voltage, that would modify it immediately in the file and have impacts down the road. But otherwise, it's a very convenient mechanism for manipulating all these JSON files that you might run across. Okay. Did that answer all the questions that you had with respect to the CTF and Defocus stuff?
They weren't very good questions, but I learned quite a bit, so thank you.
Yeah. All right. I mentioned that there is a Wiener filter in EMAN2, but I don't think it's one that would be useful in the context that we're talking about here, right? It's something that we could apply to particle data or something like that. I mean, why don't we go ahead and just finish since we talked about that thematically? Why don't we go ahead and do that? Let's see. I'll just do it with E2 display for the moment, and I think it'll be all right. Oh, no, that's fine. All right, so let's look in particles again, and we'll take a look at the full res, one of the full res stack of particles, which has the CTF information in the header, and we can run that in filter tool. And filter tool here has whatever the last set of parameters, whatever the last set of filters I put together was. So let's make a new one. We'll call it Wiener. Sorry, I didn't refresh the display when it set up the new filter. A little bug, but so let's try filter. There we go. Now it updated. Filter.Wiener2D. And it crashed. That's a shame. Let's see what it was upset about. Oh, cannot open file. Well, maybe I need to find out more about the Wiener filter. I haven't done that in a long time. To help. Wiener. Oh. Let's see, CCC, SNR Wiener, what's that one? Huh, interesting. All right, so filter.wiener2d. Oh, it expects you to pass it a CTF object. So I would think that it would take it from the header by default, but maybe it just doesn't know how to do that. Oops. Let's see, filter Wiener2d applies a 2D Wiener filter based on CTF parameters. CTF object used for Wiener filter parameters. All right. Well, let's try doing it from Python, since again that's what we're supposed to be doing. Let's go ahead and do it from a Jupyter notebook, just so we don't lose stuff. That, and then we'll just go ahead and read all the images. Data.read images, and I'll just hard code in one of the image files. Particles, so let's just go for, I don't know, it doesn't matter which one, this one. What I meant to do. There we go. Okay, so now we have all the images. There are some reasonable number of them, 20 or 30, something like that. And if we look at images of 0 CTF, we should be able to pull the CTF from the header. And you can see it's a nice convenient thing. If you pull the CTF from the header, it actually returns it as a CTF object, right? So you don't have to go through any effort of reading out all the parameters and then turning them into a CTF object. So you immediately get an EMAN2 CTF object. If you want to get access to any of the parameters, then you still can do that from the CTF object. You can like that. You can get the defocus and that sort of thing. But since what we need for the Wiener filter is a CTF object, that's particularly convenient. So we should be able to say something like x is equal to images of 0 dot process filter dot Wiener 2D. I think I got all of this correct. 0, yeah, like that. Oh, apparently not. Let me see what happened. Huh. I have no idea why the Wiener filter is crashing on us. Maybe we have to now. I know I've used this before, so it should be functional. Well, all right. I don't want to get back into another debugging session today. Let me see what the other Wiener filter processor does. There's another one, which was Wiener by FSC. Oh no, that requires passing in a Fourier shell correlation file to estimate the signal to noise ratio. This one is estimating the signal to noise ratio from the CTF parameters. Huh. Well, I'm kind of yeah. Go ahead.
In absence of a Wiener filter,
Yeah.
what would your filtering strategy be to really boost the low spatial frequency features? Make them more
boost them for what? Boost them for what purpose?
So I'm imagining like if I wanted to see the features in a tomogram or be able to pick them visually better, even with maybe some resolution loss.
Well, I mean, you could do a high pass filter, obviously. I mean,
So
you can do high pass and low pass filters, right? So if you do a little bit of a high pass filter, then you can get rid of some of the distracting gradients or other sorts of artifacts that you might have, and then you do a strong low pass filter to get rid of the high resolution noise, right? I mean, that's effectively what the Wiener filter is primarily doing, in a traditional sense anyway, is basically filtering out the noisy parts of the signal. So there are other things you can do to improve contrast for purposes of looking at images and annotating them. For example, well, I'm in BGAL. Okay, let me go back to this real quick. So there is. Yeah, I'm going to run the interactive particle picking just quickly. All right, so this is obviously not a tomogram; it's a micrograph, but it'll be serving as a proxy for our purposes, right? So when we zoom out like this, effectively we're doing a little bit of low pass filtration already. Let me clear the boxes from one of these, just so we can see the image clearly. All right, so you can see. Oops. All right, so you can see the particles floating around there. They're kind of hard to see, hard to tell what's going on. There's a button here, filter display. And you can see now that's maybe a little easier to see all the particles. You can see the shapes of some of these BGAL particles. I can turn that off again. So that sort of operation would also work probably pretty reasonably well for most tomograms, for just applying it to a 2D slice of a 3D tomogram. You're not going to, you wouldn't want to apply this kind of thing probably to an entire tomogram, because the anisotropy in Z would probably mess things up. But if you're looking at tomogram slice by slice, this kind of filter would probably be a useful operation to perform. So what filter is it using there? That is, let's see. It's got some name. It has a name, but what should I call it? It's a very unusual filter because it's not doing any. There it is. Enhance. Yeah. Filter.enhance. It doesn't take any parameters. You just call it on the image, and it will make it look nicer.
Seems like a name I should have spotted and tried.
Yeah, it's if you run the particle picking program and say, hey, what filter does that? Well, it's filter.enhance. We could see what it does really quickly before we stop on a tomogram. I'm positive whether it will work right, but we can give it a try. The issue is it does use information about sort of biology in the sense that it needs to know the angstrom per pixel value. I'm saying some of the things it does are scale dependent, so it has to have the angstrom per pixel value correct in the header for it to work right. So if we just say show 2D on the tomogram, actually, my only concern here is that, oh, that's a tilt series, not the tomogram. My only concern here is that the tomograms use negative contrast. The darker is denser convention, whereas the single particle data uses the opposite convention. I'm not sure. There may be an asymmetry in that filter, but let's just try it. We just open up the control panel. We can just go to filter. And we'll just say filter.enhance. Oops, enhance. There we go. Yeah, you can see it's actually getting rid of stuff. So let's do this. Oh, not what I meant to do. Turn off that. Turn off that. Let's
Are you just going to invert it?
I was just going to invert it.
Math.mult.
Math.invert? Or math.mult?
-1.
Math.mult. Okay, yeah. Mult -1. Yeah, that's good. Let's see what that does. Oh,
nope, I was wrong.
Oh, sorry, value equals. All right, we'll have to do some help. Oh.
Is it just mult without the math?
Maybe. Well, there's a method called mult. That's why I wasn't using that, because it's a method. It's not a processor, and I need a processor for this. There's a linear processor which we'd use scale. So I can use math.linear with scale. There's often more than one way of skinning a cat, as the expression goes. Doesn't seem to be doing anything either, though.
I wonder what the invert button is doing, because that'll do it nicely. But
oh yeah, but that doesn't actually change the data, unfortunately.
Yeah.
Shift. Maybe I have to pass it a shift as well. There we go. All right, that was harder than it should have been. So that's actually not a very pretty section of the tomogram, but anyway. Yeah, all right, so that one is, I'm wondering whether I have the angstrom per pixel value correct there. I mean, if you look at that, something funny is kind of going on. There's not much structure. Those ribosomes look almost flat, and they didn't before. All right, my filter.enhance demonstration obviously isn't working very well. Certainly, you can do a low pass filter, right? That's what I was suggesting with doing a low pass. High pass filter, just to smooth it out a little bit. And I don't know what else we might want to do. But anyway, you can see just a little low-pass filter goes a long way towards enhancing the apparent contrast of the tomogram, right? If I before and after. I think this is just not a real good example. It's been downsampled a lot, and it's, yeah. What would happen if I do that?
I'll keep playing around.
Yeah, well,
it's still
you
super
can
helpful to see
certainly
the
try
filters you're using.
filter.enhance and see what it does in different contexts. It was mainly designed for single particle analysis, but I still think it would probably, the concepts that it uses would probably still work in a lot of tomography situations.
Yeah, I was really shocked by the supposed deconvolution in ISONET, because all of a sudden we started seeing details that we just could not see before. So I'm just trying to figure out how to approximate it. I'm sure eventually I'll get there.
All right. Oh, so what you're trying to do is not replace what ISONET is doing. You're trying to just replace a deconvolution filter that they're applying as a pre-processing operation.
Yeah, that's pretty much it. They're calling it the Ctf deconvolution, and it doesn't make a whole lot of sense to me because it's doing it on the actual tomogram. But
yeah, yeah. Other than looking at their code, I'm not sure how to figure out what exactly they're doing.
No, I appreciate the time.
Yeah. Okay.
The Ctf and the
okay.
filters.
Yeah. No, I figured that stuff is also useful for some of the people in my group too. So, who may or may not have all seen it before. I mean, I know Phil's seen it before, but Eric, if he watches the recording, probably hasn't seen it in as much depth as he should have. Okay, well, we'll call that a wrap for today. And again, no meeting next week because I'll be on an airplane. But then we'll pick up again the week after that.
Thanks.
All right. Bye, everyone.